So I shared this PDF with the organizers, and they had uploaded it somewhere. I think it's that GitHub page that you. So do you all have access to this PDF that you're seeing on the screen? Yeah. Okay. So I will just go through the basically the PDF that I have here, and then I have basically sort of two sections here. So the first section is mostly about like tables and graphs, and the second section is about doing a little bit of regression and then missing value imputation. So we will break it down into two parts. In the first part, we will just do the tables and graphs, and then we will do one exercise all together. And that's when you will do the actual coding. For the rest of it, you can take note, or you can just like what is called, like you can open the PDF and just go through the PDF with me. So I'm not going to go through it in RStudio. Rather, I have the code and the output for you. I'll just explain what I have done for you. So overview, so three things to cover basically. So tables and graphs, and then a couple of two things that I will do in the second half. Now the next part I will show, since most of you is like are new to R or RStudio. So very recently, not very recently, like maybe 5 or 6 years ago, they came up with this new collection of packages that they named Tidyverse. So those of you who are completely new to R, you already know that there are a bunch of libraries that are already by default there, or you can actually import libraries, like you can install them as you use them. You can load them, you can unload them. That's totally up to you when you want to use it. So Tidyverse, it's a collection of a lot of different packages that are very, very useful. So I just took this picture. Did I put the source? Yeah, so I just took it from tidyverse.org. So they came up with, so some of those packages, they were there before Tidyverse. Like for example, ggplot, it's a very old package, but then they combined all of these things together. And how they combined it, basically they are using sort of the same grammar. Like it's the same type of table, same type of data structure that all of these packages that they follow. We're not going to use all of them. I will just walk you through a few of the options that you have in Tidyverse. So mostly the packages that I will be concentrating on is dplyr and then ggplot, like how to deal with data and how to produce different plots. In case you want to install it for the first time, you can do it from here. Or I don't know if Sohi has showed you, you can just go to the RStudio window, and there is a tab called package, and you can install it from there. Like any package, just type in the name, and then you will be able to do it. So if you don't have it right now, wait for our first exercise. At that time, we will be able to install Tidyverse and then load it if needed. So the data set that you also have, I believe Anaki has shared with you, all of you. Yeah. So the salary data set, maybe Anaki, just few sentences about the data, because I didn't know how you got the data, like where you got that data from. So maybe just a couple of sentences about the data.
Yeah, so the data set I got it from a website called Kaggle. So if you don't know, Kaggle is basically a hub for data science like projects, and like there's a bunch of data sets on there. And then if you keep up with our Instagram as well, we just launched a Kaggle competition for the NBA Games prediction. So if you go to Kaggle, I go to our Instagram, you can find more information about that, and then you can explore Kaggle as a website as well. In terms of the data set itself, it's basically a data set that consists of all the different job titles as well as the salaries for those specific jobs. And they have a bunch of other features as well, as you can see on the screen, like age, gender, education level, and so on and so on. So that's a brief overview of what it is.
Okay, thank you. So that's the data set which was shared in a CSV format, which will be the case like when you go to actual work. Either it will be in a CSV format that your colleague will share the data with you, or an Excel file, or in some other format. And all of those formats, there is a way to read it. The basic one, I think Sohi showed you last week. I looked at her presentation. So read.csv will allow you to read that CSV file. I'll talk about this option later. For now, it's just a file that was saved in the same sort of R Markdown file, and then I just read that file and named it as D. So from now on, that will be the name of my data set. First few things that you can do when you have the data set is, instead of, even today, even though I will tell you that don't do it, even today what I do is I open the data set and try to see the whole thing, which if it's a smaller data set, in this case I think there was few thousand observations, it is still possible. But when you have millions and millions of rows, it's not really efficient to open a data set. So don't open a data set, but as I said, I still do it. So this thing here, that allows you to print the first few observations. So I think it's just the first 6 lines of data, which is telling you just a snapshot of the data set, basically, what are the variables you have there and some of the observations. You can also look at the tail part of the data, just say what's the tail of this data set, and then that will print the last 6 observations for you. And this is just a fast impression one more time, since you're looking at the data set for the first time. One thing that you can check quickly, it will show up on RStudio. Like if you open it, it will tell you that there are that many rows and that many columns. But you can also get it in terms of like a code thing, that you can actually say, hey, what's the dimension of a data set? It's just a flat 2x2 table type of thing. So there are 2 dimensions there, row and column. This is how many rows you have in that, and this is how many columns you have there. And you can actually refer them either using variable names, or you can refer them using just column or row numbers, just like an Excel thing. Like, so if you say that, hey, what is D1 and 1, that's basically is going for the first row and first column observation. So you can treat that data set as a sort of an Excel file as well if you want. But that's another conversation. So here is the first sort of summary that you can calculate. To some extent, I'm not a computer science student, like I took only few courses there. So I'm not sure if you would take my words literally. Like, to me, R is a high-level language. What I mean by that is, like, if you just say, hey, what's the summary, it will give you the summary. So it's not like, you know, how to say it. Like, it's not a computer science student, help me. It's not a machine-level language. It's like really high-level language most of the times. If you want to calculate a mean, just say what's the mean. If you're going to calculate a standard deviation, just say what's the standard deviation, and it will just do that thing for you. So in that way, I'm saying that it's a high-level language. You can actually just say, hey, what's the summary of the data set? And now, if you look at it, there are a bunch of summaries that will be in front of you. In case it's a numeric variable, for example, this age, if that is the case, it will give you all of those numbers. Some of them are pretty intuitive. The first one is what's the minimum value, what's the maximum value, what's the first quartile, median, third quartile, so on and so forth, if it's a numeric random variable. If the variable is categorical, let's just say in this case what's the gender of the participant. In this case, it says that, hey, there were that many female observation and that many male observation. And it will do it for all the variables that you have in the data set. So that's another sort of, you know, check that you have there. What's the use of summary? Why should you look at a summary? Like, when someone gives you the data set, your expectation is that there are a bunch of categories should be here. Or your expectation is, let's go for this race. So your expectation is that there's supposed to be these races that you want to see in the data set. So that's sort of a quick way of checking, is it looking how it should look? Like the countries that you have there, if your colleague says, hey, this data set captures data from Australia, Canada, China, UK, and USA, that's your immediate sort of check that, yes, it belongs to those countries. I don't really have another country there. Or if they say that, you know, you have data from Australia, that thing should not be missing from your summary. So these are basically just quick checks that whatever you expect in the data, is it there or not? So that's your first summary that you can calculate, which is also the old school way of calculating summary. Now there are more sort of fancier thing under tidyverse. So for tidyverse, when you load this package, this new function will be available to you. So you can say, hey, give me a glimpse of the data. And then it will give you this new sort of summary that people use now, which not only tells you what are the variable names, but it will also give you the summaries that you can get from dimension, but also it will tell you what's the variable type. Those of you who are a little bit familiar with these wordings, some of them are double, some of them are factors, some of them are integers, and anything else there? No. So anytime it's just a continuous number, that's the double thing. And then anytime it's a factor type of data, which is like, what's the title, what's the race, what's the country. So that will be your factor variable, and then you have your integer as well. And can you convert them? Can you convert one type of data to another? Yes, of course you can convert them anytime, but that is not something I'm showing you here. And anytime you need to convert, let's just say how to convert something numeric to text, just search online. Within your first 1 or 2 search results, you will find the code that will allow you to do that. Next thing is, those of you who have done a little bit of stat by now, so frequency table is something that we always try to calculate, which is just a basic summary of how many categories are there and what are the frequencies, like how many people were there. In this case, if I were to just count, how many first-year students are there, how many second-year students are there. So this is basically telling you what's the distribution of these two categories out of your entire data set. So that is what you can get from the function called table. So the way this thing goes is that you have to say, hey, create a table based on the data set D, and from the D data set, it's a specific column, and the $ is the way in R to take any specific column. So this is saying here from the D data set, if any of you are trying to type it now, if you just say D $, you will see that on R Studio, the whole list of variable names will pop up from which you can just select on it, or you can type it in if you want. So that's your variable table of one thing. You can table any value there. It doesn't have to be numeric. So you can say, hey, what's the table of the education level? Turns out it's 0, 1, 2, and 3. I didn't have the description, so I don't know what they are. But I'm going to go with 0. Maybe it's high school, 1 means college, and then 3 maybe any sort of tertiary degree. Table of the country, you have the same thing, table of the race. So you can calculate any of them. And then the comment here that I wanted to make is table works for any type of variable. So even if you go back and then say, hey, take the age variable and create a table, it will do that for you. So it will just count how many of the ages are 32, how many of the ages are 28, and then it will print that really long table for you. Is that meaningful or not? That's a different question. But it will actually create that summary table for you. Moving on to this part here. So let's go back and let's talk about this variable now. Let's talk about this one here. So education level, right now to the software or to R, this is just 0, 1, 2, and 3. So it is just treating it as a continuous number which goes from 0 to 3, and it can be any number. Whereas if you really think about it, this is actually one level, this is another level, and then another level, and then another level. So how do you tell R that, hey, those 4 numbers, they are not really numbers, they mean different things, they mean different categories. So the way to do that is creating what we call a factor variable, which takes a number or takes something and then returns you a factor. So I will show you this line of code and then maybe try to guess it. So here, if this is new to you, that's called a piping operator. So it takes the data set, passes it on to the next operation, does it, and then as more piping you add, it will keep passing it to the next work. Those of you who are familiar with Python, I'm pretty sure they have a piping operator too. So this is all it is doing, is just taking the data set, passing it to the next function, whatever you're asking it to do. This mutate here, that's a way to sort of change the data set. What I have done here, I have created a new variable called E-level, or like educational level. That is something I just named. And here I'm saying, hey, take this variable from the data set and convert it into a factor. That's the meaning of that first line. So how many variables I have changed there? 2 of them. One is education level, another one is seniority. In both cases, I created a new variable called, and I gave them new names. And the only difference between these two is that they are now factors. So just to prove my point, if you now ask it to print the data set, like the first few observations, here you have the 2 new columns that I have just created. So if you really want to see the difference between this education level and this education level, it looks exactly the same. It's just in the background, R knows now that, hey, that's a factor variable. 0 doesn't mean 0, 1 doesn't mean 1. Like if you add 0 plus 1, you're not going to get a 2 for a factor variable. Like you're not supposed to get a 2. Maybe it will give you 1 or maybe it will give you 2. Any of you are familiar with regression? A little bit. Those of you who are new to, no? Okay. So maybe a quick review. Have you heard the term regression? Like predicting future observation? Yeah? Okay. So let's talk about this. So let's just say here you have education level as there, and then let's just say salary here. Oops. So if you do not say that it's a factor, what it will do is it will fit sort of one regression line there. It will think that, hey, whatever the increase from 0 to 1, If this is education level 0, this is 1, this is 2. So it will think that the change from 0 to 1 is the exact change from 1 to 2, and then 2 to 3, and then so on and so forth. But if you say factor, now it will not fit that regression line. Rather, it will think of, hey, this is one category, 2 is another category, 3 is another category. And that's when it will just calculate different means differently for every time. So that's the idea of getting into factor from any value there. If this was already, for example, here, UK, USA, Canada, that's already categories. That's already text there. That's already string. So you don't have to say that that's a factor. But in this case, since it's number, you have to tell R that, hey, that's a factor. Like you have to convert it. Another type of variable that you will have to convert is, I don't know if you guys are familiar with this type of variable. Anyone wants to share what's the ordinal variable? Maybe people who are a little bit familiar with stat already. What's the ordinal variable? No one? I'll give you an example. I don't know how many of you have already seen this in a doctor's office. When you go there and then say, hey, I have pain, they will give you a scale from 0 to 10, and they will ask you, what's your pain scale? Circle it, like 0, 1, 2, 3. So that 0, 1, 2, 3, yes, it looks like it, but it's not regular numbers. That's an ordinal scale where you have an order. Or let's just say first year, second year, third year, fourth year, there is an order there. But if I tell you that, hey, there's just 4 different colors, there's no order there. So if there's an ordinal variable somewhere in your data, you will have to tell R that, hey, that's an ordinal variable. And it's not that it's just R that will require it to know. All the software, because to the software, these are just numbers. So you have to tell it that, hey, that's an ordinal variable versus that's just a pure regular numeric number. Okay, so enough with factors. Same idea. So glimpse of D. Now this new education level and new seniority, the 2 variables that I created, they are actually factors, which previously it was an integer. And then where's the other one? This was an integer. So that's one sort of conversion that you can do when you have just numeric numbers and you want to convert it to something else. Next thing I have for you is how to create what we call cross table. So cross table is a summary table that summarizes 2 or more variables for you. So let's keep it basic and let's do a 2 by 2 table, or like a 2 variables, 1 in the row, 1 in the column. So in this case, it's a table thing. So you want to call it table, but the table will be calculated based on these 2 variables. So I want to see the distribution, if you want to call it, or the frequency table or the frequency distribution of these 2, like gender with education level. So gender, since is the first one, those categories are here. The second variable, the categories are there. So that's your basic counts of it. Anytime you have a table like this, probably the next thing you want to do is where you want to calculate the proportion. So in this case, you can say, hey, what's prop.table? Once again, high level language, you're just saying what's prop, like proportion.table. But here, the argument that should be there, that has to be a table. So you have to say that, hey, what's the proportion based on this table? That's the meaning of that. And if you don't say anything, then this will be the proportions that will be calculated for you, which I don't know how many of you are familiar with frequency tables. This is just getting the total for the table and dividing all the numbers by that. So relative to the grand total, what percentage of observation falls into the first category? That's your percentages that you have here, which we also call joint probability. Moving on to calculating it just for the row or just for the column. So let's just say you want to calculate the proportion, yes, but only for the females or only for the males. Or let's just say you want to calculate the proportion only for this category or only for that one. So any of the row or column wise operation will be in R using these 2 things, margin equals to 1 versus margin equals to 2, where that 1 by default, at least for R, that 1 means row, and then 2 will always be the column. So in any dimension, it's just go with R and C. So R comes first and C comes 2. So the second dimension will be there. And then you will have your proportion. Anyone wants to summarize maybe one of this table? What can you tell from this table? Yeah, it's based on the columns. And then look at the numbers, what inference can you make? It will add up to 100% for sure. So each of the column will be. But what is really like, how do you interpret it? Like what's the message that you get just based on that one table if you look at it? So let's talk about this. So if you just take it, I'll make it up. Let's just say this was high school, right? So if you just take the high school ones, then there were 57% or 50, roughly 58% female, and then 42% male there. Yeah? So make the same inference for all four of these. Do you see any pattern? Do you see any connection in that table? Which was a little bit weird, to be honest, when I first saw it. Yeah?
As a whole, I would infer that males tend to get higher education.
How did you infer that? Let's talk about it.
Because, well, for males, they have more in the 3 category and the 1 category.
Okay.
And the females have more in the 0 and 2.
Okay.
1 and 3 is bigger.
Rest of you, do you agree with him? That these two, I don't know what they are, but in these two cases, there are more male participants in this data set. I don't know if it's the complete data set or not. I don't know if Anaki actually made a snapshot of that one and then made it like, a smaller table. That's a different problem. But just based on this, looks like in 1 and 2, there are more males, and then in 0 and 2, 1 and 3 is more males, and then 0 and 2, there are more females. Okay. Moving on to types of graphs that you can produce. So we will solely use the ggplot package, but there are other packages that you can do for drawing. So in and itself, ggplot has its own grammar. I'll be very honest, it took me quite some time to really realize or understand what's ggplot, like how the grammar works. So in this case, the first thing I have here for you, those of you who don't know, that's just an histogram, which is telling you, how many observations you have into this range of salary, whatever the salary variable is. So how I created this, so I said that, hey, take the ggplot function, that means asking it to plot it, and then based on the data set. So take the data set, create a plot. What would be the plot based on? So here what you're saying is like, what's your x variable or what's your y variable? So all those parameters that goes inside that AES. If I'm not wrong, that stands for, English is not my first language, I think it's called aesthetics or something. So that's that AES. And then you're saying that, hey, on that graph, X should be the salary column and nothing else. You haven't really defined anything else there. And then finally, the plotting part here is that second part. So the first line, if you look at it, that is just setting up the plot for you. And the actual plot command is this second line, which is putting the histogram. And geom is just the one code word for ggplot. So you say, hey, create a histogram. Here I have two different things there. I have said, hey, what's the color of the histogram and what's the field color? So that blue here, I don't know if it's visible to you, like the outlines there, that's the blue, that's the color. And the fill is basically the inside part of each of the bean. And I'm just going to assume you know how to read a histogram, but maybe another way of looking at it instead of just reading it. Any comment that you can make just based on this graph? So those of you who are new, this is very simply the whole range of salary. And it is just telling you in each of these categories, not very visible. I think this is 100K, this is 200K. You just take different range there. All it is telling you how many people were there in that range. So looking at that graph, overall, does it say anything? Yeah? Seems just random. Okay, sure. Any other comments? Short of uniform, okay. All right. Maher here? Seems trimodal, that's a good one. So it looks like there is one peak here, another peak there, and then another peak there. Yeah, you can say that. But as you have seen that you actually can describe it many different ways, graphs are actually subjective. you can actually read graphs in multiple ways unless it's too obvious. For example, if this was what we all really like instead, like if this was a curve like this, then it's an obvious thing that, hey, that's just a normal distribution or a unimodal distribution. So even in that case, you can argue that, hey, that is not looking like a normal, rather it is looking like a triangle. So graphs are usually, if you just look at it, usually it's a bit subjective. And then to remove the subjectivity, you need to do other type of analysis. So one more time, I'm not trying to show you here what to do, rather I'm showing you what can be done. Like these are the tools that you can actually apply. So that's your basic idea of histogram that you can calculate. The next thing I have for you is the very same thing, but with a different code, which is called density. So the density histogram is taking back now, since we deal with stat all the time, we actually try to convert everything into probability scale. So that is what we call the density curve, or the curve that actually transforms into probability for us. So in this case, if you don't try to do it, but if you actually, there was a way to calculate the area underneath that curve, that would be equals to 1. Like that's your 100% chance. So it's just converted everything into probability and then had the curve drawn there. And even though that sounds fancy, but really all it is doing is just changing the scale of this variable or the count variable, and then very simply trying to put a smooth curve on top of your data. And hence you have that roughly trimodal or bimodal distribution there. So this could be the first thing that you can start with. Usually those of you who have a little bit of exposure to stat already, usually when we try to deal with a data set, the very basic things we do it based on the assumption that it's a normal distribution. So if you just look at it, just the salary itself, probably it is not a normal distribution. So let's try to now dissect it. Let's see if this is the distribution for all other categories. For example, I know there was male and female. Is it the same distribution for male and female? There was seniority there. There was education level there. So let's try to break this thing up into different categories now. So in the next line that I have for you is, I think, maybe I'll allow you to read the code and then tell us what it is doing. Instead of looking at the output, just looking at the input itself. So still I'm creating a ggplot based on the data set D. And this time, in terms of the parameters, I'm saying, hey, salary is going to be the x-axis. And then the color is going to be this. Those of you who still remember, this was the variable that I created based on seniority. Yes or no, that's just a factor that I created. And then I also say that, hey, fill is equals to yes or no. So those two things, color and fill, I made that a function of those two variables. And then finally, I have a density plot for two of them. Would anyone like to read the plot now? What is the plot saying? Like, what do you infer from the plot? Yes, Sophie. Sorry, this is not male or female. This is just whether the person is senior or not. That's my guess. Like seniority is the variable. So the seniors, they have more sort of the higher salaries than the junior ones, which is very expected. The inference from this is this: yes, the data has face value. It's not really doing anything crazy. You expect the seniors to have a different distribution. But if you look at the distribution now just with one category at a time, they don't have the exact same distribution that you had before. So that's actually a combined version of all the things. Now you have just broken it down into two pieces. Let's break it down into more pieces if I have done it. Yeah. So now you have the education level there. So it's the same graph. I took all those numbers up, and then I have just divided up into different education levels. So the same code here, ggplot based on a data set, you have the salary, and then this color variable and the fill variable are there, which is from seniority. Now I changed it to the education level. One quick comment about this alpha thing. So that alpha here, that stands for transparency. Like if you want to make this graph transparent. If I didn't have transparency, what would happen is looks like the blue one is on the top. So you would just see the blue one. That thing underneath there, you won't be able to see that just because of the blue color. So that's why when you put alpha equals to 0.5 or any fraction like 0.2, 0.3, it will make this thing transparent like all the curves just so that you can see all the pattern. And that's why you have that next 4 things. You can actually, if you zoom in, you will be able to see all those graphs. Looks okay? Those of you who are completely new to ggplot, the first line is going to be the same for any plot that you have. Like it is going to be ggplot based on a data set, and then you have to give all the parameters that you want to give it. What's your x variable? What's your y variable? What's your color? What's your fill? I really hope that you understand the difference between color and fill here. So here, color stands for just the outside of it, and then fill stands for what is actually the fill color of that. So you can change both of them. Okay, what do I have next? Next type of plot that I have for you is creating a box plot, which is a very typical type of plot that we do. One use of it is it will tell you what's the distribution of the data, but the other use of it, it will tell you if there is an outlier in your data or not. Like if there is an observation that is extremely high compared to rest of the observations, or if there is an observation that is extremely low compared to the rest of the observation. Same idea, same package, ggplot based on a data set D, AES, y equals to, I'm just creating it based on the age variable, just as an example, and then just say, hey, create a box plot. Maybe a quick question. What do you think will happen to this if I change this code and go from y equals to age to x equals to age? In that code in this line, I want to change it from y equals to age to x equals to age. Yeah.
The x-axis will refer to the age and the graph will turn 90 degrees.
So the graph right now it's looking vertical. It will just become horizontal at that point. And it's just totally up to you. There's no right or wrong way of plotting these things. It's like, what do you prefer? Okay. Next thing I have for you, also a box plot, but this time a box plot of age as a function of education level. And then this is also something I thought, like, it's pretty expected that people who have the higher level of education, I think they're more older because education requires time. And there are some missing values here as well in all of these cases. And at any point, if you have any question, feel free to stop me. Okay, so we covered histogram, we covered density curve, we covered box plot. Now, let's learn one more thing that can be done, which is how to filter data set using any condition. But in this case, I will just use these conditions here. That here there were some sort of extreme observation. I just want to see what those extreme observations are. Who are those people in the data set that has a really high age, even though it's not really that high. It's like 60 or 62. I'm not too far from there. Okay, so let's go to here. So this is how you filter data. Once again, it's just an, if you want to filter it, just say, hey, filter. And then whatever the filter is, you put that condition inside the filter thing. So once again, you take the data set, you pass it to the next person, and then up until now, if you just take a look at that part, you have a filtered data set where age is greater than 55. So all the observation for which age is greater than 55, you have it that way now. And then you use another piping operator to pass it to the next person or the next task, and the next task is sorting the data set. So you say, hey, sort the data set in the descending order of age. And then that will print this sort of output for you, or the head of it. There are 39 observations where there. To be honest, this data set is very, very clean. They're not really, outliers, but you might see outliers in real life when you actually, filter them using any of the filters. Is outlier always a bad thing? Not really. So let's just say in a neighborhood, there are a lot of, regular people, and all of a sudden there is a surgeon there living, just one person. For that one person, if you just look at the income level data, it will be, his or her income will be like, really high compared to the rest of the neighborhood. Is that a bad thing? Not really. Will it change your summary measures? Like if you calculate the average, yes, your average will be highly biased. Like that's not the true average for that. But does that person really reside there? Yes. So if you have outliers in your data, go back and check. One or two scenarios probably will happen. The first one is probably person who entered the data is just entered it incorrectly. In most cases, outliers are just coming from like, data entry error. So that you can go back and then, ask the person, whoever came up with the data, ask them, hey, is this the correct observation? Is it supposed to be that high? If they say yes, then sure, just use it in your analysis. But if not, you have the chance to go back and then, re-enter the data in the correct format, and then you do it. I don't know if you have, like, you guys have looked at any real life data now. For example, I used to work at a place where there was a column age, and then there will be a bunch of numbers there for individuals. So let's just say 32, 35. And then in case there was a missing value, it was their organizational level sort of decision that they would put 9, 9, and 9. When they look at it, they know that it's a missing value. But when you analyze it without looking at it, that's an extremely high observation. So when you create this type of plots, that's your basic sort of way of looking at it. It will immediately tell you that, hey, there are some extreme outliers. Go back and then check. I had to learn the hard way just to know that, hey, 999 is their missing value. That's an organization level. At different organizations, they have different codes. There are some of other interesting things that you will face. I don't mind sharing one with you. For example, there was one data entry operator. His or her favorite thing to do was, if there was a missing value, that person used to write that this is missing, like in this. Like they will, it's an Excel file, so they will say this is missing. Anyone knows what will happen if that is the case? Like if you enter the data that way. What happens when you read that column? Any guess? This is a, let's just say, Excel file where you have a bunch of numbers, and then all of a sudden it says this is missing. Yeah? Unfortunately, it will not show any error. It will just read that whole thing. Yeah?
All of the data in the column turns into a strings?
Yeah, the whole column turns into strings, where this 32 will be read as this, 35 will be read as this, and then the this is missing will also be there, thankfully. So this is something that, where would you learn that, hey, this has happened? Probably the first glimpse of your data. Age is supposed to be a numeric variable. Why is it a string? Is there any way to change it? Yes, of course you can change it. Either you can go back to the source and change this, or there is a way to convert numbers into real numbers as well. So there are ways to do it. But these are something you will probably see in real life when you go and deal with data, where people have birthdays missing, or they will write the day and the month, and then in the bracket they will say year is missing. You don't have to do that. There are codes for that in every organization. Okay. What were we talking about? So filtering. So all of these codes right now, I didn't put them in one part, but I just want to show you what are things that you can do. Like by now I have shown you how to do filtering. I have shown you how to do sorting, and totally you can sort it based on multiple variables. So just say arrange and then keep putting different variable names into the comma, comma after comma. And you can filter anything there. I don't know if you have covered this before. So let's just say you want to filter using multiple variables. So you can say, hey, filter for age is greater than 55, and then just keep adding the filters, and another condition, or and another condition, or in R is that one line there. I don't know what it's called, like it's somewhere on your keyboard. So or stands for this, so this is or, and this is and. So you can put any number of conditions in your filter, or you can put any number of ascending or descending variables that you have in the arrange statement. Okay, let's continue with the next part, which is how to create summary tables. So summary tables here in dplyr or in tidyverse, the way it goes is you have to say summarize and then just calculate whatever you want to calculate. So in this case, if you look at the data set, I'm grouping my data, or I'm grouping my summary by these two variables. So I'm saying, hey, give me a summary table by gender, by education level. And then for each of those categories, give me the first variable, I named it counts. Give me how many observations I have there. Give me the average salary, and give me the years of experience. I'm just creating random tables here at this point. So if you look at the output, the first two, like gender and education level, so you have female education level 2, and then you have your average salary and average experience. And similarly, you're all 4 different categories there. Anyone knows why only I have this many observation there? Why do I have? Yeah. So I'm just using the outlier data set. I'm not using the entire data set. So whatever I have filtered here in D2, that's what I'm using to create that summary table. You can use any table you want. You can use any data set you want. So this piping thing, this can be applied anywhere. Like for example, you can do this and then say that, hey, yes, I want this very same table. Maybe you guys can help me. I want to sort this table based on, let's just say, this average column. How do I do it? Yes, I want to see this table, but I want, what's the biggest number here? 19.7, is that the one? I want that to be at the front, and then similarly, this thing in the order. How can I change this code so that this output will be changed based on whatever you have seen so far? One option, can I save this whole thing, call it D3, and just sort D3? Will that work? So D3 is just going to be this table now, where you have these variable names. And I can say, hey, take D3, arrange it by average salary in descending order, which I have shown you how to do here. Any other way I could have done it without creating a new variable? Yeah.
It's the same way you did above. You just pipe it onto the.
Yeah, you just pipe it onto the next thing, and then say arrange by whatever you have created here. So you can keep on piping as you like, and then you can just keep passing it to the next operator that you want to. Yes. Okay. Let's move on. Next type of plot I have for you is it's called scatter plot, or very simply, it's just a plot of x comma y. There will be a x, like continuous number on the x-axis, continuous number on the y-axis, and you just want to see the relationship between those two variables. The example that I have here is if I take age and salary on the y, age on the x-axis, I just want to create a scatter plot, which is just put the points, nothing else there. So I put this ggplot based on d, x is age, y is salary, and then geom underscore point will create this point for you. A very sort of quick question for you. Any guess? In total, I think we had almost 6,000 or 8,000 observations. In this picture, does it look like there are 8,000 observations there? If I'm plotting x comma y for all of them, which is if I take the age number, take the salary number, I point them each of these points are on this plot. Does it look like there are 8,000 points there or 9,000? Probably not. Any guess what's happening here? Yeah, Sophie. So there are a lot of plots there which are basically overlapping or very close to each other. It didn't even plot the whole thing. So if you want to get the true picture, maybe geom point is not the thing that you should be going for. There's another function called geom jitter, which will make it more sort of spread out. And in this case, I also used another variable there. I said, hey, not only give me the scatter plot, but color it by the gender variable. So this time you have the two different colors, red for the female and for the male. And also I have used alpha equals to 0.5 just to show you that here there are multiple points. For example, I think I was talking about which one it is. Let's talk about this one. There's multiple points there, but if you go back, look at the previous one, there was just 1 point there. So unless you have this alpha equals to any number, like if you put alpha equals to 0.2, it will be even more transparent, like it will be really light. So that's one way to show that you have all the plots. Any comment based on this curve? Like if we talk about the relationship between salary and age, I'll give you a couple of options. Does it look a linear relationship between salary and age? Is that a straight line-ish relationship? Senior people are saying yes. Freshers are saying no. So if you really want to force it, sure, you can think of a straight line. But if you really allow it to pick it, probably it will be picking something like this or some other curve. Okay, we'll figure that out. So let's go to the next one. So now I'm just, if you ask me why did I created all this plot, there's no reason for that. I'm just showing you these are the options that you can do. Like you can add many things into the plot part. So right now I had the very same plot, but this time I'm saying, hey, use gender as the color, but then use education level as the shape. So now you have this very same plot, more complicated. These symbols are there to show you that these are the education levels, and then you have the male and females one there. If I were to zoom in a little bit, anything surprising there? This was age, this was salary. Yes, Mark. So here, yeah, this was the sort of surprising part. There's mostly males, which is a little bit surprising. Yeah, so a lot of females CEOs there too, who make a lot of money. Okay, moving on. The next thing I want to show you is how to sort of have the same plot now, but let's just say break it down even more or dissect it even more. So here I have the very same plot that you have just seen, but this time different plots for different countries. And that you can do using this last command, which is called facet wrap, which is basically wrap it or break it down into different countries, which is giving you this Australia, Canada, China, UK, and USA. Sorry, I'm torturing you guys. Any comment based on this one? Or I will give you the question. Is there any variation that you can see between the countries? Yeah?
Even like some countries like Canada, there's more non-free education levels at like kind of the very end, like the age and salary, but in some other countries, like it's kind of just the plus ones.
Okay, sure. Yeah, that's an interesting one. When I looked at it, I was like, okay, that looks almost similar to me in all 5 different countries. So, yeah, but if you really look at it, there are some observations here which are basically taller than the other people there. Or there may be more concentration on the left. But this is other thing. What else can you put there? So you have color, you have shape. You can also put size there. Like what would be the size of those bubbles or symbols. You can change that too. You can make that a function of variable as well. I didn't think I put it there. This is another sort of use of facet wrap. Now I'm not just wrapping it around just country. I'm saying, hey, country with seniority, just as an example, random plot here. So not only you have the 5 countries now, but for each of the country you have the seniority 0 versus 1, 0 versus 1, and then it continues. So you can actually create all of these plots. You can continue plotting it. The things that I'm showing you in maybe last 40 minutes, this is supposed to be your, let's just say at least a couple of weeks of work. Like you're supposed to look at the data set, you're supposed to dissect it, you're supposed to do many sort of the summaries, and then you come up with your final sort of modeling idea. What variable should be modeled, whether you should keep it as continuous or whether you should break it down into different levels. Okay, so the GZ plot. Anything else I had there? No. Explore package. Okay, let's get through these 2 and then we'll go for the exercise 1. So this is something I really just learned last week while working for this. I was searching for different things like different data set or different examples. So I learned about this new package which is called Explore, which by default does a lot of those plotting thing using just one line code. So if you're completely new, probably you will like it. So you just load the library, and in this case, so I'm saying, hey, for this data set, explore the salary variable for different gender. And that creates this plot for you, which previously you had to have a ggplot, and then you have to have the salary, and then you have to have, in this case, color or fill, both as gender. So this is just, it's just a replacement code for you, which is saving you a little bit of typing, basically. So it's still doing the ggplot part. If you ask the same thing for a categorical variable to a categorical variable, it creates this thing by default, like it creates what they call a bar plot here, where you have the numbers for each of the gender. Moving on to this, so this is another thing that I figured out, that if you just say explore all, it will basically create all the summaries for all of the genders. Like, so all of your variables, there will be some sort of summary. If it's a continuous variable, it will be a density. If it's a categorical variable, it will just be a table or a bar plot. So that's just a one-line command that will give you this whole thing. I don't know why when I was putting it in R Markdown, it was printing it in this color, but if you do it in a what do you call it, like interactive session, it actually produces that plot. So I don't know when I put it in the PDF why it was colorless, but this is the plot that you're supposed to get. You can actually zoom in and then look at many of the different plots. So that's like one line thing that will create all of these plots for you. And then if you like any of the plot, if you want to know more about it, you can actually draw it manually by yourself. Sounds okay? One more time, I have never really used it. It's just a package that I found just this weekend. And the good thing about R and Python is that people are working on them like regularly. So you will have these updates on a regular basis. Another problem that I face a lot is that, let's just say it might happen in A57 in the winter, that I will tell you, hey, this thing doesn't work in R. And then one of you will tell me that, hey, it works. And it's just because the last time I did it, it didn't work. Now it is working. Because people have changed it. People have new codes now, new packages now. So they get updated a lot. Okay, so that's Explore package. Next thing I have for you is correlation. Maybe since a lot of you are new. Anyone wants to share what's a correlation? Or what does it do? Up are your students? Yeah?
As one variable rises or falls,
Mm-hmm.
the other variable rises or falls.
So correlation is the measurement of that relationship. So whether X and Y are related or not. But there's sort of a technicality there that correlation only looks at linear relationship. So it only tells you is Y a linear function of X or not. So it only looks at linear relationship, and then it will spit out some numbers for you. The higher the number, the higher the correlation that you have there. It can be plus and minus depending on his example. Like if X increases, if Y decreases, you're supposed to get a negative number. But if both of them are increasing or decreasing at the same time, you're supposed to get a positive correlation. Okay, so the package that will allow you to plot correlations is what we call the core plot. And this is the code here that I have for you. And here is the plot basically. So it is giving you what's the correlation between age and age, which is not really meaningful. There's a correlation of 1. But these other bubbles, that will tell you what's the correlation between those other variables. And you have a scale there. The scale goes from 1 to -1. I didn't have any other value there. So mostly it was positive correlation. If you don't want colors, rather numbers, you can also ask for just number. And it will produce this number thing for you. So it will tell you that, hey, correlation is 0.73 versus 0.81, and so on and so forth. The color also changes on that number. So that's your correlation. I think that's what I had for the first part, like tables and graphs. I have a tiny exercise for you, not based on this data set. There's another data set in R, which I will ask you to do. So maybe since this is 6 of 15, I'll give you 10 minutes to work on it. So just write these 2 lines in your R Studio that will load the Boston dataset for you and try to do this task. Just basically just asking you to reuse the code that you have seen so far. So try it. We'll be here. The organizers are here. And then I will show you. And if you don't want to do the exercise, that's okay too if you want to take a break. So let's come back at 6:30. And I'm here if you have any question, feel free. what I have on the screen, it's probably not correct. So correct me. That will probably be best learning. So the first one says just load the data and then take a summary of the data set. What are the values are there? So the Glimpse will probably do that for you. Let's talk about the next one. So I have a ggplot for made v, and I want to do a geom density. But the color variable, would that be the chess thing? And I haven't created factor yet. Like I haven't converted it into factor. So let's see how that plot looks like. It is this. Is it the color or the field that I have asked you guys to change? Making separate densities for it. Okay, so this time color is one of them and fill is also that. So there you go. In this case, that's weird. I was expecting at least 2 different curves, but since it is not there, that defied my purpose. So let's call it d Boston is equals to d Boston mutate, and then let's call it chess n. Okay. So the first line converts it, and then now if I do this new variable now, will it show the correct plot? And is that something what you guys got? Yeah. Okay. And how do I make it more transparent? Alpha equals to 0.5. Okay. What was the next thing? A scatter plot of L state and made v, and then color and shape, both of them. So this is the new variable. This is the new variable. Sorry, not geom density, sorry. What am I doing wrong? Sorry, it's not chess. Does that plot look okay? Did we all get the same plot? Yeah. Okay, all right. And the last thing was the correlation one. I just tried it from my memory. So library core plot, do I have it here? What is the library called? CORRPLOT. CORRPLOT. Okay, the core plot is loaded, and then core plot core dataset, core plot core dataset. Okay. Oh, I have the factor variable there.
Not making no sense.
Anyone else having trouble there with the last one? You guys are having trouble as well?
Oh, I had the same error, but just reverted to the previous version of d.boston.
Right. So since I have created a categorical variable there, like a factor variable there, it doesn't know how to calculate correlation for that variable. So if I can get rid of that variable from the data set, so that will also work. So this is sort of the old school way that I just want to get rid of the last column, want to keep all the rows, so I can get rid of the, how to say it, get rid of the last column of this data set. From that part, I want the second thing, such as, let's see if that thing works or not. Okay. Will I be able to zoom in? So now you have a plot showing a lot of different things there, which will tell you, which are the linearly related variable, how much linear relationship you have there, and from there on you can actually proceed to your next step. Sounds okay? Yeah. Okay. All right, so let's go back and then let's finish the next part of it. So, sorry? For the last question. So I'll tell you what happened there. Since I created the factor variable, I'll show you. So it was not working there. So what I have done there, if that code doesn't make sense to you. So this is the row and column for the data set. I just removed the last column. That's the whole thing there. There are other ways of doing it, more clearer ways to do it. Like for example, you can say select. Let's show it here. So you can say, hey, this is the actual data, which is from D Boston. You can say select. But then since you want to remove it, just say minus, and I named it as this. And that will do the same thing for you, basically. So you can do that. It will remove the factor variable that I created, and then finally just create the whole thing based on D. Sorry? I'll repeat it. So this whole thing, that's like how we used to code during our undergrad. We didn't have tidyverse. But now it's like, this is more a readable code. That from the data set, just remove one column there. And then create the correlation matrix based on that. Okay, let's very quickly move to our second part now. So if I'm not wrong, in the next workshop, Professor Demarest will go over the statistical inference. So I'm guessing he will be going over linear regression and all of those things. So you will learn these things in more details, in more explained way. The next set of idea that I have for you, this is also exploration, looking at relationship, but just one variable at a time. So suppose, I don't know what was the actual problem here, probably it was about predicting salary. So you wanted to predict salary, or you wanted to fit a regression model of salary as a function of rest of the features. So in this case, all I'm trying to show you is how to look at one variable at a time, how to look at salary as a function of age. Since you are feeding a linear regression model in R, the code is going to be just LM, which stands for linear model. And then you can save it under any name. Let's call it M. And then you can say, hey, what's the summary of that model? And then under that, you will have many different outputs, which I think Sartorius will go over. But I will just show you a couple of things from there. So basically here I'm asking it to fit a regression model of salary over age. And in this case, these two numbers, that's the intercept and slope of the line of best fit, or the regression line. Once again, you will learn them in details later on, but this is just giving you an idea that, hey, if you want to force it to be a linear function, then that linear line starts at here, and then this is the slope of it. One more number without any interpretation is that this value here, that is telling you that, hey, that relationship that you have just forced, that's actually really a significant relationship. So now that number being really close to 0 is telling you that, hey, that slope over there is definitely not 0, which is another way of saying salary and age is really, really significantly related. So that's sort of one indication for you that, hey, I can actually start with age and put it in my final model of prediction or feature selection, however you want to call it. Moving on, if I do salary as a function of gender, now I will take you back and just to show you that gender was, so there were two categories there, male and female. So if you look at the output here, yes, you have an intercept, but then for the slope part, you have just one category, male. So since you have categorical data, what this thing is doing, it is actually taking one group as a reference. So compared to the female group, the one that is missing there, how much more the males are making on an average. That's that number, which also can be seen as a linear regression as well. So in this case, it is saying that, hey, in this data, if you just compare female to male, the male people are on an average making that amount of money more than the females. And that relationship is highly significant. So this is just a couple of ways of reading it. Let's do one more model. I'll take you back one more time for those of you who are like completely new. So when you fitted a model of salary on gender, in this case, gender was like there were two categories. You got the output as this, where one of the categories is missing, which is the reference category, and then the number that you have here corresponding to male, that is just comparing male to female. If you got that part, let's just say you have never learned regression before. Will you be able to read this output that, hey, I have fitted a salary, like regression model of salary on education level. Remember, education level was 0, 1, 2, and 3. Here is the output. Can anyone explain this output to me? What's the meaning of this number? I'll help you. What is the category missing here? Education level. 0. Like education level 1 is there, 2 is there, 3 is there. 0 is missing. So that's your reference category. And then this number is telling you that, hey, people with education level 1 on an average make 60,000 more than the education level 0. Same idea. Education level 2 makes 95,000 more than the education level 0. And this is the education level 3 versus education level 0. All of these numbers, they are significantly different from 0. So we're just telling you all of these numbers, they're actually, they're not insignificant numbers. They're, there is a statistical significance in all three of them. So are the education levels, like, do they affect salary? Sure. Is this something we expected? Of course. Okay, moving on to salary by country. Probably this is where I wanted to see the relationship. That, hey, between the countries, there's not really any variation. Like none of these numbers, they're very close to 0. Like if there's a number that is close to 0, I hope you can see the pattern. There will be some stars there. So since the stars are missing, that means none of these things, they actually matter much in terms of one to the other. Any guess what these numbers are compared to? Canada, China, UK, USA. Yeah?
Australia.
So all of these numbers, they are compared to Australia. So this is what's the average salary in Canada compared to Australia. What's in China compared to Australia, UK and USA. You probably have got this already. Why Australia? I didn't ask it to take Australia as the reference. Why did it take Australia as the reference? In the first case, I didn't ask it to take education level 0 as the reference. I didn't ask it to take the female as the reference. Why is it taking female education 0 or Australia as the reference category? Whatever is the first category, yeah. So after sorting it alphabetically, whatever the first one, R takes that by default. Can you change it? Yes, you can always change what's the reference category. Will every software take the first one as a reference? No. Other softwares will take the last one as the reference. It's just whoever wrote the code, that's how they wrote the code there. Okay. All right, so you got the idea here that you can actually compare the relationship of one variable with another variable one at a time. When I say the first thing that the graphs are subjective, yes, you can read graphs differently, different people. But these numbers, they are not subjective. They're basically hard calculation of estimate based on all your actual numbers. Moving on here. So based on whatever I have checked here, looks like age, gender, education level, all are significantly associated with salary. And then country probably is not. There's not a lot of variation among different countries. And as I said, I have only fitted 4 of them. You can fit as many as you want. And then you can sort of tweak it. There are multiple ways. There are more, automated ways that will check all this model for you. But I'm just showing you that these are some starting points that you can do. So Sartorius will go in details about the relationship. Now, the next thing I have for you is how to have ggplot show you the relationship. like the data-based one, not something that you sort of put it. So if you don't force it to be linear, if you just say that, hey, give me a smooth line based on whatever relationship you have found in the data, just add that geom underscore smooth. It will tell you that that blue curve over there, which is not looking like, I don't know if it's visible to you, it's not looking like a linear relationship. So when you really fit it in your data, don't just stick to linear term, maybe try some other term as well, like a quadratic term of age or a cubic term of age. So that's something you can get it from here. Those of you who are familiar with splines, you can put splines here as well. Like any sort of non-linear relationship, you can actually put that into that equation. Okay, what else did I have there? All right, the last bit for us, which is if there is a missing data, how do you deal with it? Which is, to be honest, a little bit advanced compared to whatever we have covered so far. So far we have just looked at basic tables, basic graphs, and then basic linear regression. Missing value imputation is actually, in a lot of undergrads, they don't even learn it at the undergraduate level. Like they learn it in the graduate level. So missing value will happen everywhere. Just as an example, the one that I gave you, age is missing for whatever reason. People didn't report their age. Income is another variable. You will see a lot of missing. People don't want to report their income for whatever reason. Some people think that if they write it somewhere, CRA will come and then ask for taxes. That's how they think. But maybe that is not the case. Some people don't answer it because of their status. Maybe they want to say that their income is low. Or maybe some people, they don't want to say that their income is high compared to the rest of the neighborhood. So there are a lot of different reasons why you will have missing data. In this case, we technically didn't have any missing data like the one that you just did in the exercise. So Anaki actually, I think, went back and randomly removed some of the observation just to show you how a missing data will look like. So that's why you have the second version of the CSV file there. So let's read that file. It's the same read.csv. And then in this case, I will take help from another package which is called NANIAR, which is the missing sort of missing data package for R. And then if you just say, hey, give me a missing variable summary, once again, just a high level line, it will tell you that, hey, these are the variables you have in the data. That's how many missing observation you have there. As you can see, these are really nice numbers. Like there's only 1,000 missing values and then 500 missing values. That's because Anaki forcefully removed 1,000 and 500 observations randomly there. And this is just telling you what's the percentage of observation that are missing there. Nothing really concrete here, but the rule of thumb is in practice. If the percentage of missing is more than 20%, you are in a big trouble. You should not be using that variable or try something else. But if it is less than 20%, then try some of these methods that you will be seeing in the next 10 or 15 minutes. So 20% is sort of the cutoff for missing value. If you have more than that, don't try to impute it, because it's at that point you are making a lot of assumptions. You can not only get a table, but also get a picture which uses ggplot as well. So it's called ggmisvar. And then that will give you a missing value summary based on some random variable that you have there. So in this case, I created a summary for male versus female and what are the percentages of, or what are the number of missing values for each of the variable that you have in the data, which once again is just a quick overview of summary. If it is too much, probably nothing that you can do. But if it's a tiny amount of them, you can actually do some of these options. So here are a few options that you can do when you have missing value there. One is remove the row. I don't mind drawing it. For example, when you have a data set with, let's just say, 9 columns. So let's just say these are the 9 columns. And suppose this number is missing, but all the rest of the numbers are there. Some other row, let's just say this value was missing, but all the rest of the numbers are there. So one way to do it, you can just remove this row completely from your data set. That's one way to do. Another way to do is, if there's a lot of missing value in just one column, maybe get rid of that entire column. Both of these things, they are not recommended. You should not be just removing observations just because 1 or 2 values are missing there. So that's your option 1 and 2, which is one called na.omit, which will remove all the rows for you. And then you can also remove the variable that has a lot of missing values in there. Both of these, don't do it. The next thing is very common thing that people do is when you have a missing value, replace it by the average of that entire column. So a naive calculation. In this case, let's just say years of experience was missing for this guy. So what this code will do, I will let you to see it for a couple of minutes and then maybe explain it to me, what am I doing here. So in this code, I have asked it to calculate something based on this column, and I have created a new column which I called new years of experience, or new YOE, which gave me this column. So can you just read it? It's not something that you know beforehand. You have to know that this is exactly how this calculation should be done. So one more information there. So NA is what we call missing here in R. So NA stands for missing. So this thing here is NA, that's like a condition. Is it missing or not? So if the years of data is missing, I'm doing something. If not, I'm leaving it as it is. So what am I doing if it is missing? I'm replacing it by the average of the entire column. If you try to calculate the average without this thing, it will not work, at least for R, because it will try to calculate the average of all of these numbers. There is one missing there. It won't be able to calculate the sum. It won't be able to calculate the mean. Hence, you have to say, yes, calculate the average, but remove this missing values. So that's na.rm, that stands for missing, remove. T just stands for true. Either you can say TRUE or you can just say T. Question, yeah?
Yeah, so do you have to cover every case? Like, could you just not put the second line? Like, it just doesn't do anything, it's not missing? Or you need
This one here,
cases?
the only reason I did it because I created a new variable. That's why I have it here. Like I named a new column. If you're just doing it for the original one, yes, probably you don't need it. If you're just changing the original one. So how did it got changed? So this was the average for all of them, and that average was like this NA was replaced by that average. That's one option that people use. Those of you who are familiar with median, a lot of people use median versus mean instead of getting the mean. So those are some ways you can replace them. Do you have to do it case by case? If you're using this, yes. But there are more fancier packages that does it automatically. You just have to say that, hey, change them by the age. These are the columns that you need to fill them in. And then it will do the very same task for all of those columns. So that's one thing. The last thing I have is a little bit of a fancier package that will do all the imputation task as part of just one package. Please take a look at it if you have time, or when you actually do like real type of imputation. So it's called simputation or S-imputation. So in this case, you would calculate, what is it? YOU. Yeah. So let's call it D2. And then in this D2 case, I'm asking it to impute using a linear model. Why am I asking it to do that? Let's go back and then let's talk about this guy. So yes, its years of experience was missing. And then I wanted it to replace it by the average of everyone. Let me ask this question. Was everyone same in this data set, or they had different sort of characteristics that you have? So their years of experience is probably not just average of everyone. It is probably a function of the salary, the country, the race, and the seniority as well, and all the rest of the variables. Point I'm trying to make is you can actually guess this by looking at all the rest of the variables. That could be one guess. The other guess is you don't want to look into any of the variables. You just want to say, hey, replace it by the average. So this is also estimation. This is also you are guessing, but it's a, how to say it? It's a naive guess without looking at any of the things. But in the next page, that what you have there, that's sort of a more of a fancier thing. That yes, I'm asking it to guess it, but guess it as a function of age, salary, gender, education level, country, race, senior, and everything. So looking at all of those values, calculate it, and then in this case, here is the value that is estimated. So if you compare it to the previous page, now it is saying, hey, the years of experience for this person, it should be 15.72, which previously, if you just look at the average, it was just 8.03. Which one is more accurate? I'm just going to go with the second one because that actually looked into many of these different variables, and then literally it's just feeding a regression model predicting the observation for that particular thing. Can you do it for all the variables? Yeah, you will be able to do it for all the variables, and that's how it will be estimated. Those of you who are a little bit senior, you have done a lot of regression by now. Any priority you have in terms of having this salary there? Purely for the senior people. I'll break it down for you. So the original purpose of this task, of this analysis, was to predict salary. So you want to figure out a model for salary. Sounds okay? In this case, I had missing value. I'm imputing that missing value using all of these variables. Should I have salary in that model or not? Should I use salary to predict the years of experience and then use this imputed data to predict salary again? So there is no really right or wrong answer to that. Some people use it, some people don't use it. You should not be using it, the reason being is sort of double dipping, because you're actually using salary to predict years of experience, and then years of experience will be used to predict the salary. So that's one of the reasons why people don't want to use it. Some other people say, hey, a relationship between y on x is not same as the relationship between x and y. It's a different sort of relationship. It's a different sort of prediction. So I don't have any answer whether it should be used or not. It's totally up to you. So that's sort of the thing that I had there. All of this cable thing is just producing this plot nicely on R Markdown. But going back, missing value imputation, this is just probably, the whole thing is just tip of the iceberg that I have shown you today. If you just want to teach one course on ggplot, it's possible, an entire course. If you just want to teach one course on missing value imputation, there is actually courses, just one entire course on missing value imputation. So I have just shown you a couple of really basic things that can be done. But this package is very, very powerful. Take a look at it when you have a chance to the actual documentation. I don't know if you have learned how to check documentation. Just search online, say simputation package R. There will be a bunch of PDF files which will tell you exactly what can be done in those packages. We'll stop here. You have an exercise, very tiny little one for you. I'll ask you to take a screenshot, or I will just load it on the different part. I will have to go in 5 minutes. I'll have to pick up my car. But otherwise, if you have any question, I'm here for next 5 minutes. Yeah, go ahead, Sophie.
How do you install the SIP package?
It's the same way you install any other package. So go to the package tab and then search for simputation and then just say install. Okay. If you have any question, I'm here. Otherwise, thank you so much for coming, and good luck with your data exploration. I will see some of you in the winter again, some of you in this term, in this course. Yes? Do I use R in B57? Those of you who have taken courses with me, they would know I use R in every course. Even if there is nothing to show, I will still use R to show something. So yeah, I use R in every course. All right, so let's stop the recording here. But I will be here if you want to try. Thank you so much, everyone, and thanks to the organizers as well.